Okay, well here's our unit, hot off the presses from JLC PCB. Got all the components on one side here, and this large area here, which is alternating power and ground traces. We'll look at a little closer. And yeah, not a lot to this. We'll be going over it in detail here. So now for a little closer look here. We've got our power feed here, 9 to 12 volts kind of. A fairly large filter cap here, a 5-volt regulator, a LED indicator, our AT Tiny 85, the currently chosen power transistor here, a 10 millihenry coil, diode rated at 800 volts, 0.02 microfarad at 1 kilovolt capacitor, and our neon lamp coupling to the grid here. Neon lamps on real flimsy leads, so we hot glued it to the capacitor for support. Here's a closer look at our grid array, our inductor, our neon bulb. To do the layout was a little tricky getting the KiCad to accept connecting this to these points here. So we had it feed just a couple isolated points there, and then it seemed to be okay to bridge it. So what we have here is alternating power and ground. So this is power up here, goes to alternating strips, and the ground here is likewise connected at the bottom. So these are pretty damn close together, and the idea is any bug walking across this is just sure to straddle them. By the way, on my workbench I've accidentally touched this thing with my arm while working with it, and it was hot. And although in theory that's a rather high voltage, the connections are so close together that it doesn't send a shock through your body. It can only go through a small area of skin, so it just feels like an annoying, I don't know, little tingle or something. Almost more annoyance than anything else. So this is probably pet safe. Nothing of any size stepping on this will get much. But if you're an insect, and I'm not sure all the viewers I have, but just in case, then your body is rather small, and you might have one leg here and one leg here and another leg here, and you're just going to get your ass zapped is what's going to happen. Here's our picture of what's going on in the unit. We're running 100 milliseconds per centimeter here. This is what generates the pulse. We'll have to expand this to show you what's going on. These are a series of short on-off pulses that will kick spikes out of the inductor, and this is the resulting voltage generated, 100 volts per centimeter. 1, 2, 3, 4, 5. We got 600 volt pulse here at the capacitor. Now we'll take a closer look at what's going on in here. These pulses are about 100 microseconds followed by 100 microseconds off, driving the transistor, and here's where the voltage spike occurs. Now by experiment, changing this time and this time, we found the optimal range for generating the best looking spike here. Leaving this on for longer than it takes to saturate the inductor simply wastes power, which is bad news because we want this to run on batteries if we want to. And then you need a certain off time here. Now, to tell you the truth, I'm not sure why it doesn't happen immediately after that, but, well, there it is. Okay, now we're going in really close here to look at that spike, and we're at 5 microseconds per division here, so basically this is like 3 microseconds. So it's still at 600 volts, but it's only about 3 microseconds. That's why we have to accumulate these. It takes quite a few of these to start charging up the capacitor. Okay, going back to our earlier image, now that we understand what's going on in here, there's actually 500 of these spikes, and it takes about, let's see, 100 milliseconds. Takes maybe 20 milliseconds to reach a full charge. And just by arbitrary design, we decided to leave this power pulse on for 100 milliseconds here. It turns off and discharges through a couple resistors and very quickly goes down to 0 volts here. So here's our device running on the AT-Tiny85. Typical 9 to 12 volts coming in J1, 5 volt regulator, usual filter capacitors, kind of extra large one here because this thing draws a power spike when it's active. Got an LED indicator here, but mainly what we do is out of pin 3 here we have a 150 ohm resistor which pushes the limit of how much current this can put out here, driving a transistor that's selected to have a high voltage rating. This one's rated at 800 volts. Basically the procedure is you turn it on, wait for a certain length of time to get a current flow in inductor L1, and then quickly turn it off, which causes a voltage spike because that's what inductors do when you stop feeding them power. That's a positive voltage spike here, which goes through D1 to charge C3. Now these voltage spikes are very narrow, and it takes quite a few of them. But the on time here is, I believe, 100 microseconds, and off time is 100 microseconds. The pulse itself is only 3 or 4 microseconds. But they'll accumulate here, and this entire thing runs, we'll see on the scope, for 100 milliseconds. So you get 100 milliseconds of a high voltage here. Now this zener is to prevent any of the original 12 volts from leaking through here and going on this grid array between the pulses. What that will do from experience is glue in insects not to walk on it, because they'll sense that 12 volts. So I originally put like a 16 volt zener here so that when this is not creating a voltage here, that the 12 volts is blocked. But I found a neon lamp works kind of better and is real surefire, as they say, because below 60 volts this thing absolutely does not conduct anything at all. So with the high voltage generated here, we do lose 60 volts going through here, but it does isolate this. Alright, well, here's the program made for an AT-Tiny85. H volt is the pin that turns the transistor on. We're not currently using this. In theory, this device can read back the voltage and regulate it to a lower voltage continuously if we want, and LEDs on that pin. We turn on some of the pins. Basically, we turn almost all of them on except that sensing pin, which we're not even using now. This is a command that sets up the watchdog timer. All of this is created from the document file for the AT-Tiny85. I kind of just look up the registers, check all the bits in order, and just use one command to set them all at once. Then we also deliberately set the LED. This turns the LED on. The bit set and clear commands are way more convenient to use than those ugly looking shift, rotate, put it in concoctions I've seen people use. So yeah, these are documented right in the Arduino. There's bit set, bit clear, bit write, and bit read. They're very handy. So here's basically the code. I mean, this is more or less it. We do 500 iterations of turning on the transistor, waiting 100 microseconds, turning off the transistor, waiting 100 microseconds, and going back through the loop. So 500 times a total of 200 microseconds leaves 100 milliseconds, or a tenth of a second. So after we're done, we turn off the LED just to give a nice indicator, and then call sleeper. Okay, to save battery power, so I can run this on a 9-volt battery, I go to sleep between the voltage spikes. And I've chosen a 4-second time here. I'll let the bugs walk around a bit before I zap their butts. So this is the command to set up for a 4-second on the watchdog timer. And here's some commands to set the sleep mode so that when we power down, we'll power down entirely. I'm not sure this one's really needed, but it turns off peripheral clocks. And then the only way I know to get to sleep is do an assembler command, which is kind of tidy. SM sleep, new line. Okay, that executes the actual tiny 85 sleep command. Well, it actually never comes back from this routine, because the way this wakes up is we're using the watchdog timer, and watchdog timer is set to reset the chip. So it actually goes here and just waits until the 4 seconds is up, and then just starts over. Comes in here, does a few things, turns on the LED. So this is a lot simpler to do than setting up one of the counter timers to do an interrupt and do this stuff. Besides, we automatically get watchdog timer functionality. Should anything like screw up in here, it only waits 4 seconds, and then boom, it just resets and starts over. Alright, as usual, all the dirty details are available from the links below to my GitHub site, including a zip of the Gerber files. And just so you know, I was using JLC PCB, and these boards cost me, I think, a little over $2 a piece. What a deal. So there you go. Hope you like it. In the future, I may show you a live demo if I can find some bugs. So other than that, have a nice day.